Hello, good morning students. I am Dr. Sunita Tandon from RR College Alwar. In the last chapter which we have started yesterday, I have delivered a lecture on formation of ozone layer. This unit is the third unit of your syllabus of environmental chemistry. Now today we will study the mechanism of ozone depletion. Ozone can be depleted by following processes. First is natural processes. Atmospheric oxygen absorbs ultraviolet radiations at less than 240 nanometer and photodissociation into two atoms. These atoms unite with oxygen to form ozone. During the process, surplus atom of nascent ozone is often transformed to nearby molecules by kinetic energy, which raises atmospheric temperature. Ozone can also absorb short wavelength ultraviolet radiations in the range of 240 to 320 nanometer, releasing atomic oxygen. This natural mechanism, however, does not necessarily upset the ozone equilibrium because the loss of ozone is compensated by the creation of ozone through atmospheric circulation. Now, the second method of ozone depletion is anthropogenic activities. Anthropogenic processes responsible for the depletion of ozone layer share a general mechanism of the type X. Reacting species reacts with ozone to form XO and oxygen. This XO molecule which is generated combines with oxygen atom and forms oxygen molecule, and regeneration of X takes place. And the total or net reaction gives oxygen plus oxygen atom plus ozone plus 2 oxygen gives 2 oxygen atoms. Ozone layer is destroyed in the varying degree or by free radical species such as HOX. HOX we can say free radical, OH free radical, HOO free radical. Similarly, by NOx radicals, that namely NO free radical, NO2 free radical, and similarly CLOX radical means Cl free radical and CLO free radical, etc. First, we study the hydroxyl radical or HOX cycle. The hydroxyl radical are formed by following photochemical reactions. First है oxygen free radical reacts with water molecule to form two OH free radicals. Similarly, water absorbs quantum of energy and absorbs one quantum radiation and is converted into H free radical and OH free radical. The production of OH free radical is largely due to natural processes. These hydroxyl radicals composes ozone. First, OH free radical combines with ozone to form oxygen and HOO free radical. HOO free radical combines with oxygen atom and forms OH free radical and oxygen. Next cell reaction is oxygen atom combines with ozone to form two oxygen molecules. Similarly, in case of hydroxyl radicals, H free radical combines with ozone to form OH free radical and oxygen. This OH free radical combines with oxygen to form H free radical and oxygen, and net reaction is oxygen atom combines with ozone to form two oxygen molecules. Third is the nitric oxide cycle or NOx cycle. The effect of NOx emission on the ozone concentration depends critically on the altitude of emission. Thus, NOx emission in the mid and upper stratosphere will lead to net ozone destruction. However, a net increase in ozone layer is predicted in NO is emitted into the lower stratosphere and upper troposphere. NO molecule, nitric oxide molecule, reacts with ozone to form NO2 and oxygen. The NO2 form now reacts with atomic oxygen to form nitric oxide plus oxygen, and the net reaction is again one ozone molecule combined with oxygen atom to form two oxygen molecules. In the lower stratosphere and upper troposphere, the oxygen atom concentration is smaller and photolysis of NO2 to form oxygen atom and then ozone form becomes complicated. So NO2 absorbs one quantum of radiation to form NO and oxygen. In the next step, oxygen combined with oxygen atom plus M to form ozone plus N. In the stratosphere, N2O undergoes photochemical decomposition to NO, which in turn depletes the ozone layer. So N2O reacts with one quantum of radiation and is converted to N2 plus O. Similarly, N2O reacts with oxygen to form 2NO, and then NO reacts with ozone to form NO2 oxygen. The main photochemical reaction in this dissociation of NO2. NO2 absorbs one quantum of radiation and is converted into NO plus O. The NO2 form may be oxidized by ozone or slowly by oxygen, leading to cyclic chain reaction. The chain may be broken only when the NO2 is completely converted into HNO3 by hydration and catalytic oxidation in presence of aerosols, fog, or photochemical smog. The reactions may take place in the following sequence. First, nitric oxide with two molecules, they react with oxygen to form 2NO2. Then NO combined with ozone to form NO2 and oxygen. Then NO2 forms two molecules of it react with ozone to form N2O5 plus oxygen. Then four molecules of NO2 react with oxygen and two water molecules to form 4 nitric acid. Similarly, N2O3 plus water molecule gives 2 nitrous acid HNO2. HNO2 and HNO3 may also undergo photochemical dissociation. HNO2 absorbs quantum of radiations to form NO2 and H3 radical. HNO2 absorbs one quantum radiation and converts it into NO plus HO. Both are possible. And then HNO3 absorbs one quantum and forms NO2 plus HO free radical. In the stratosphere, NO2 may react with HO free radical forming HNO3. NO2 reacts with HO free radical and forms HNO3. Thus, NOx increases the rate of ozone destruction with no change in the concentration of nitric oxide. The supersonic aircraft SST discharge large quantity of NOx in their exhaust gases directly into the stratosphere. Hence, there is possibility of doubling the NOx concentration, which in turn will tend to reduce ozone level by about 40%. Nuclear explosions produce large quantities of NOx, which are injected directly into the stratosphere. Nuclear tests conducted by USA and CIS in the early 60s reduced ozone content by about 40%. The estimate value of NOx in the stratosphere is 3 to 5 into 10 to the power of 9 molecules per centimeter cube. Recently, it has been found that hydroxyl radical is very efficient in removing NOx from the stratosphere. Thus, the observed depletion in the calculated ozone concentration may be 2.7 per oxygen distribution. Now, the third third thing which is responsible for the ozone depletion is chlorine radical CLOX cycle. Ozone is the stratosphere is also found to be destroyed by man-made chlorofluorocarbon CS chlorofluorocarbons and halogens. These are widely used in air conditioning, aerosol propellants, cleaning solvents, plastic foams, in dry cleaning and in fast food packaging. The extreme chemical stability and non-toxicity of CFS called freons enable them to persist for years in the atmosphere and to enter the stratosphere. In stratosphere, CFCs are subjected to photochemical dissociation by intense ultraviolet radiations. First, CFCl3 Chlorofluorocarbon absorbs radiations greater than 290 nanometer and is converted into CFCl2 free radical and Cl free radical. This CFCl2 free radical absorbs one quantum of radiation and converted into CFCl free radical and Cl free radical. CFCl free radical absorbs one quantum radiation and is converted into CF free radical and chlorine free radical. And then chlorine free radical reacts with ozone to form ClO free radical and oxygen. ClO free radical absorbs one atomic oxygen to form chlorine free radical and oxygen. The net result is regeneration of chlorine free radical, which sustains chain reaction from first to last. It is known that the one chlorine atom can destroy 1 lakh ozone molecules. CFCs have lifetime of the order of 100 years. In September 80, scientists reported a large hole in the ozone layer over Antarctica where ozone layer depleted to 30%. CFCs were the prime suspect for causing ozone destruction. Antarctic hole appears during Antarctic late winters and early spring. The reason why this occurs are related to the normal effect of NO2 in the chlorine atom catalyzed destruction of ozone by combining with ClO. ClO reacts with NO2 and forms ClO-NO2 chlorine nitrate. But these NOx gases in Antarctica are removed along with water by freezing in the polar stratospheric clouds at temperature below minus 70 degrees centigrade as HNO3.3 H2O. Furthermore, chlorine species can be liberated from ClO.NO2 and other chlorine compounds such as HCl by reaction in the cloud ice, followed by photodissociation to yield ozone destructing chlorine. ClO.NO2 react with water to form HOCl plus HNO3. ClO-NO2 reacts with HCl to form chlorine and HNO3. HOCl with HNu to form HO free radical and Cl. Cl2 reacts with HNu and form 2 chlorine atom. The destruction of ozone by chlorine involves an intermediate ClO, which should be observed if Cl is the cause of ozone depletion. Again, volcanoes inject chlorine and HCl directly into the stratosphere. Chlorine on exposure to ultraviolet radiation, that is 300 to 400 nanometer, forms chlorine free radicals, while HCl reacts with HO with OH to give Cl. By reacting with Cl4, Cl free radical is trapped as HCl, which is retained out in the troposphere. Cl free radical reacts with CH4 to form CH3 free radical and HCl. The reaction of ClO free radical with NO2 to form chlorine nitrate ClO-NO2 stable product is significant since it reduces catalytic cycle of chlorine and NOx for ozone destruction, thereby lowering the overall oxygen depletion rates. Bromine from halogens can also replace chlorine in the cycle and destroy ozone level. BRO react with ClO free radical, form bromine free radical, chlorine free radical and oxygen. Similarly, bromine free radical generated in this react with ozone to form BRO free radical and oxygen, and this Cl free radical reacts with ozone to form ClO free radical and oxygen, and the net result is 2 ozone is converted into 3 oxygen. This is the cause of ozone depletion. Methyl bromide used as soil fumigant. It is also a potent ozone depletion substance. Bromine compounds are much more reactive than chlorine analogues in terms of ozone depletion. Thus, ODP value of halogens like bromochlorofluoromethane CF2ClBr, bromotrifluoromethane CF3Br, and dibromotetrafluoroethane CBrF2 are 3, 10.10 and 6.0 respectively. Thanks. Next we will study on next lecture.